So I'm going to show you a couple of questions here about the intersection of two planes. What I want you to do, read the questions, pause the video, have a go at them and come back and check your answer against what I'm going to show you. Here is my working. So here you go. First question is about proving two planes either intersect or are parallel. So how do we go about doing that? And the second one is finding the equation of the line of intersection of planes, but giving it in all three formats that we know of the equation of a straight line. So pause the video and have a go at both of those. Now the first one, determine if the planes with these equations are parallel or intersect. Well, the first thing to note is that if the two of them are parallel, the vector product of their normals will be 0. There will be no vector product of their normals, so there will be no line that is parallel to both. We will not have a direction vector for our line of intersection, so therefore there will be no line of intersection. So let's look at those. So let's examine, and we'll say normal 1 is the intersection of the first plane, and I'm going to say that that's 6 to negative 2 just by inspecting it. And our second normal, n2, that's going to be given by negative 3, negative 1, 1. If I then look at the vector product of the two of them, I'll do my little matrix table here. Plus, minus, plus. First row is n1, so 6 to negative 2. Second one is negative 3, negative 1, 1. And I'll just do my cross product as I normally would. So look at the row and column, take that out. I get 2 times 1, which is 2. Take away negative 1 times negative 2. That gives me 2 as well. In the I, I'm then going to take away, if I get rid of the j's, I've got 6 times 1, which is 6. That's going to be take away negative 3 times negative 2, which is 6 in the j direction. I'm then going to have plus in the k direction, 6 times negative 1, which is negative 6. That's then going to be take away negative 3 times 2, which is negative 6 in the k. Lo and behold, 2 minus 2 is 0, 6 minus 6 is 0, negative 6 plus 6 is 0. So that is equal to 0. What that means is the vector product of my two normals gives me 0, so it doesn't exist. I cannot get the direction vector of my line of intersection, therefore the two planes are parallel. So that's how mathematically we prove it. You could look at it straight away and say it is without proving it. So if I were to look at the two of these vector normals here, what I could say is that n1, well, that's the equivalent of doing negative 2 times the n2 vector. If I multiply everything by the negative 2 in here, what that is that gives me the exact same normal as the first vector, as the first plane, sorry. So what that means is the two normals are multiple equivalents of each other, so there can be no vector product, so they're parallel. So you could look at it and say that to yourself straight away and say, right, this is what I should get, and then mathematically prove it using the vector product just to back up your assumption based on this fact here. So a couple of ways to look at it, a couple of things to think about in this sort of task. Second question was find the equation of the line of intersection of the planes given by these two planes here in all three formats of the equation of line in 3D space, vector, parametric and symmetric form. So first thing we need to do is find our line, our point on the line, sorry, and then our direction vector for the line. So for our point on the line, we'll set z equal to 0. If I was to do that in both of these, I get 4x plus y equals 4. And I'd also get x plus y equals 1. Now because the coefficients of y are the same, what I'm going to do is just subtract them from each other, as I normally would with simultaneous equations. I'd get 3x is equal to 3, so x is equal to 1. And if I substitute that back into here, what I'm actually going to get is that y is equal to 0. So what that means is a point on my line is going to be given by 1, 0, 0. So there you go, we've got a point on a line from that. Point to note is that if I was to do it so it was in the xz plane and set y equal to 0 to begin with, I get the exact same point here of 1, 0, 0. What I then have to do is get the direction vector of my line. And in order to do that, I take the two normals to the plane. So I'm going to say that n1 is 4, 1, negative 2. And the n2, my second normal, is going to be given by 1, 1, negative 1 there. And I'm going to take the vector product of them. So n1 cross n2. And we just do it as normal. So I've got my I, my j and my k, plus, minus, plus. I've then got 4, 1, negative 2. I've got 1, 1, negative 1. And I can just do as I normally would. So for my I, take out the row in the column. I've got 1 times negative 1, so I'll get negative 1. Take away 1 times negative 2. Take away negative 2. That's in the I direction. Then going to be take away from my j again. Rows and columns. 4 times negative 1, so I get negative 4. Take away 1 times negative 2, so it's negative 2 in the j direction. And then my final one, plus for the k, 4 times 1 is 4. Take away 1 times 1, 1 in the k direction. So what that means is my direction vector, let's call that A, that's going to equal negative 1 take away negative 2. So that's negative 1 plus 2, so that's going to be I. I've then got take away negative 4 minus minus 2. Well, minus minus becomes a plus. Negative 4 plus 2 is negative 2, but it's a minus outside, so it's then going to be plus 2j. And then this one here, 4 minus 1, let's hope we can do that by now, gives me plus 3k. So that there is the direction vector of my line. So now I can put it into all three forms of my equation. So I know for the vector form, I'm going to have x, y, z. Now remember that equals that equals the point plus t times the direction vector a. So what that's going to equal is 1, 0, 0, so my point on the line, plus my parameter, let's in this case call the parameter lambda, times the direction vector 1, 2, 3. So there's my vector format. Let's mark that clearly. So vector. I can then use that to write down my parametric form. So I'm going to have x is equal to 1 plus lambda. Y is just equal to 2 lambda. And z is equal to 3 lambda. And then I can use that to get my symmetric form. So what I'm going to do is I rearrange each of these, so I get lambda equal, and then I can write them out. I'll end up with x minus 1, and I'll put over 1, just remember to have that there, equals y over 2 equals z over 3. So there you go, that's the equation of my line in three-dimensional space, which is the line of intersection of those two planes, given in all three formats of the equation of a line, which we've covered. It's a fairly straightforward process. We just have to remember the steps and remember the properties associated with it, and hark back to the line in three-dimensional space material that has been previously talked about in other videos.